Methane. What goes into your mind when you hear that? Is it the thing that cows fart all day? Is it a natural gas that you put on some of your heating appliances? Is it a greenhouse gas that's 20 times more potent than carbon dioxide? Or is it a molecule with a carbon atom that has 4 hydrogen atoms attached to it? Methane is all this and more. But more importantly for today, I'll let you in on a secret. You can also use it for rocket fuel. But first, why methane for rockets? To answer this, let's talk first about kerosene and hydrogen, two of the most popular rocket fuels today. Kerosene, particularly RP-1, is the most popular fuel used by rockets today, with launch platforms like the Roscosmos-Soyuz and the SpaceX Falcon 9 using this extensively. It is derived from jet fuel, has high energy density, is reliable, proven, and very easy to store. Hydrogen, particularly liquid hydrogen, was identified by all the leading rocket visionaries as the theoretically ideal rocket fuel. Hydrogen has the highest enthalpy release in combustion and produces a specific impulse of up to 450 seconds. It is commonly found in the second stage of rockets as it works way better in space, but was also used extensively in the space shuttle. And then here comes SpaceX and their talk of using methane for their brand new Starship. Now, methane is closer to kerosene than hydrogen, which allows methane fuel tanks to be smaller than liquid hydrogen tanks, but not small enough to offer significant performance benefits over kerosene. Switching from kerosene to liquid methane necessitates increasing fuel tank volume, which negates the increased specific impulse. Methane is simply in a middle ground between the most popular and proven fuels, kerosene and hydrogen, where its performance is better than kerosene but not as good as hydrogen. From the perspective of rocket developers, in the past decades, why would they use the middle-of-the-road methane when hydrogen gives better performance overall? It simply wasn't worth the effort. However, SpaceX is changing all that. And with the use of methane on their new Starship, which was designed not just for rapid reusability, but also for long-term missions to Mars and back. The crux of it all is that methane can be made on Mars. With all this talk of a new fuel, there will also be a need for new engines that can use methane. We can't just simply repurpose kerosene and hydrogen rocket motors. Brand new ones have to be developed. So, how do scientists and engineers come up with ways to design and optimize these engines? Answering this question is especially important for the creation of new methane engines, as although there have been developments by the United States and Soviet Union before, not much really came out of it. Brand new developments, like by SpaceX, have been mostly done in-house, which is quite the feat.
Fuel for space missions has been a constant and ongoing research for improvements and innovations by space industries. The cost of access to space has always been a challenge for the government and space agencies alike to propose to decrease the price but still be reliable and effective for commercial missions. Currently, the space sector observes a noticeable evolution towards a competitive commercial market, initiated with a price raise imposed by new private companies. With this, space agencies have been developing innovative research for fuel that is cheaper and reusable. This is the focus of our video, a piece of research released in 2021 entitled Chemical Modeling for Methane Oxy-Combustion in Liquid Rocket Engines.
So currently, for liquid rocket engines, a new fuel technology replacing hydrogen fuel has been promising recently, which is the methane fuel technology. Methane fuel brings the advantages of high density, good specific impulse, and lower cost for production and storage. This technology has been present in Prometheus, Raptor from SpaceX, and in the liquid natural gas or LNG family. Over the past few years, testing of these fuels began in computer-aided analysis or simulations that are highly accurate as technology advances. One of the most popular and emerging methods in conduction simulations with high complexity and accuracy is the computational fluid dynamics, or CFD. CFD uses computers to produce quantitative predictions of fluid flow based on the laws of conservation, energy, mass, and momentum. In most research, CFD is the numerical analysis of fluid dynamics problems. However, the quality of numerical simulations can be further increased when considering turbulence. If turbulence is evident in a flow, it appears dominant over the other flow phenomena. Therefore, in conducting CFD, it is important to consider turbulence monitoring or turbulence modeling. One of the most common turbulence modeling are the Reynolds average Navier-Stokes, direct numerical simulation or DNS, and large eddy simulations or LESS. The three turbulence models are almost the same and only vary between high accuracy and computational cost. Though accurate, RANS is the least from the three, but with the lowest computational cost as well. DNS, on the other hand, is the most accurate between the three, however, it also has the highest computational cost. LES or LESS lies between the two parameters. Therefore, in terms of practicality, it is the most used turbulence model. LESS has become extremely popular in the hardware modeling space. Some applications include internal combustion engines, aerospace engineering, wind turbine design, and even in marine energy. By leveraging computers, we can theoretically test thousands of possible designs prior to building a physical prototype, in which we can save some form or some of our energies and even in time.
Despite the advancements of CFDs, there are still limitations of assessing and understanding the bigger picture of numerical solutions. Specifically, the complexity of pollutant chemistry and combustion that entails additional molecular kinetic properties are not fully accounted for in CFD. The use of direct integration of detailed chemistry in accurate turbulent combustion models are very much at high computational cost, in which it compensates for the feasibility of each solution. With this, scientists introduced the newly analytically reduced chemistry, or ARC, that represents an attractive compromise between accuracy and efficiency. Hence, what is ARC? ARC is a knowledge-based compact mechanism retaining only the relevant kinetic information as extracted directly using specialized reduction techniques. Therefore, deriving an ARC scheme is valid for future LRE technologies is the first objective of this paper. In derivation of analytical reduced chemistry for methane oxy-combustion, the methodology part of this paper, in which the authors benchmark from the works of GRI 3.0, RMAC, and Slavinskaya that provided good candidates of chemical schemes. These schemes are made from methane oxide combustions at high pressure. In this study, they used the chemical scheme that is made for high pressure methane oxide combustion with several reactions added for each specific condition. This was then validated against low diluted methane oxide shock tubes experiments in order to follow LRE conditions. The reduction is performed around a pressure of 49 to 59 bar, just above the critical pressure of both propellants. This is important in order to sufficiently reach the supercritical combustion regime with an injection temperature of around 280 Kelvin. For the chemistry reduction, it goes with the several steps within the automatic algorithm. First, direct relation graph with error propagation, or DRGEP, is performed several times. This is to keep only the most relevant species and reactions. Second is chemical lumping, which is applied to remove isometric molecules. And lastly, the level of importance criterion is applied in remaining species. This is to select the ones to be treated with QSSA. Now, to control the reduction process, the total heat release rate flame property is the primary target. This parameter controls the flame stabilization and flame length, which are essentially used for engine design. Lastly, for the validation part, the ARC scheme is validated on laminar diffusion flames.
For the results of this study, The flame shape is shown through the following images that represents the results for the test bench conducted for this study. These images contain various average fields, comparing the two integration methods, where a typical diffusion flame shape anchored at the lip is easily recognizable. As observed, the central flame is shorter, and it seems that the side flames are slightly bended towards the walls. Also, the main exothermic zone of the side flames is shorter, next to the walls due to the colder area near the walls. The flame structure is studied through the scatter plots realized in the red box. The red box shown in the figures in the time average solution. The figures on the screen display the instantaneous fields of the temperature with superimposed streamlines. Corner and inter-injector recirculation zones appear with different sizes in the axial direction. Short flames and fast thermal expansion lead to a thermally homogeneous flow of hot gases about 3,500 Kelvin and downwards. But at the figure for the instantaneous CO max fraction field, the burnt gases composition is less homogeneous due to the different relative positions of the flames. CO is trapped in the corner recirculation zone but entrained downstream by the accelerated flow between the flames. As a major control parameter of diffusion flames, strain rate statistics are represented in the following graph. Analyzing the flame structure, statistics of the time average heat release rate in the mixture fraction space is presented as follows, wherein both the time average and the standard deviation in this zone, defined with the red box of the previous figures, are plotted. The two AVBP computations are again very similar. However, due to the time averaging operation, the complex shape with the two exothermic and one endothermic peaks. For the propellants CH4 and O2, AVBP results fit correctly the Cantera laminar flame solution with little dispersion. The main products H2O, CO, and CO2 show more discrepancies. In particular, the CO-CO2 equilibrium is slightly moved. Smallest species like CH3 and OH, they exhibit larger differences compared to the laminar flame. In all those figures, note however the perfect match between the less class and less expo case, demonstrating the validity of the exponential time integration method.
Now, the paper shows the derivation for the analytical reduced chemistry scheme for lab-scale liquid rocket engines. This allows for a strong reduction and associated computing time gain. Because of the extreme flow conditions, the complex structure is well retrieved with minimal species and reactions. It is now possible because of the derivation code arcane. Now, despite the reduction, the analytical reduced chemistry scheme remains stiff. This leads to prohibitively small computational time steps for large eddy simulation. To overcome this, a new integration method was proposed. It ensures positive concentrations and reinforces simulation stability. Now, even with the stiff ARC, the constraint is relaxed using a small computational time step. This allows for better study of the chemistry in the flame. The complexity of the flame structure shows the need to use detailed chemistry for the configuration. With the test cases, the integration method used allowed for a decrease of computational cost while keeping the same quality of simulation. The analytical reduced chemistry and exponential integration method make large eddy simulations possible for methane oxy-combustion with accurate chemistry and realistic liquid rocket engine configurations.